Okay. Ready? You guys are dropping like flies. All right, welcome to EE123 Lecture 19. Woo! A to D, practical ADC and digital to analog conversion. It's my time now. Okay, so we finished talking about polyphase decomposition. We talked about multi-rate. Now I want to go back and touch about some issues related to practical implementation of ADCs and DACs. Okay? Digital to analog conversion and analog to digital conversion. Because nothing really, the model that we had so far is relatively ideal, right? Ideal filtering, ideal, there was no quantization involved. And I think it's, as people that will use signals at some point in their lives, most of us will, I think it's really important to understand actually what an ADC or a DAC could provide you and how they're implemented and what are the limitations and what the issues are when you are obtaining real samples or trying to produce, again, real samples. Is there a noise? Is that better? Yeah. If it happens again, let me know, okay? Because it's going to show on the recording. Oh, I know why. Bad phone. It's my phone. I think that was doing this. Okay, so there's interference. Right? They're not even transmitting on the same frequency, but it was saturating the receiver, right? So these are kind of real effects that are happening, and you have to understand that when you are dealing with digital signals, because nothing is perfect, really, in the real world. So we talked about the case of ideal anti-aliasing, right? You have an analog anti-aliasing low-pass filter that perfectly selects a bandwidth for you. Then you sample it, which effectively evaluates the continuous time signal at t intervals. Okay? And then followed by a quantizer. And why do we need a quantizer at all? Can't we just keep it continuous? No, right? We got to represent something on a computer, so we got to quantize it somehow. Either we quantize it using integers or floats or something, but it's going to be quantized. Okay? All right, so the model there, we have some spectrum, which is band limited, but if we sample it it doesn't actually have to be band limited, but if we sample it at a rate which is lower than twice the highest frequency, or, twice the highest frequency, so we're always going to define, and for the lecture today, we're going to define omega sub n to be the Nyquist frequency. So the highest frequency. So twice the highest frequency, then you're going to get aliasing. Okay? So that we saw before. And so what you do is, in order to avoid the aliasing, you run your signal through a bandpass filter, a low-pass filter, that would filter out the high frequency that would alias, and now the signal is band limited to the bandwidth that can be represented by the rate that you're sampling. And you don't get aliasing anymore. Okay, so you don't get aliasing. So this is in a perfect world, right? But obviously, that is never going to happen. Because to produce such a sharp filter, you need a really, really long delay. Okay, you really need lots of taps. And of course, your signal changes over time, so it's not going to be stationary. So that's it's just not going to work. Okay, so there's going to be some roll-off in any real system, and that roll-off means that there is going to be some aliasing. And I showed it to you when we did this SDR. Right? The SDR, we assume, we get 2.4 megahertz of bandwidth, but in fact, the edges of the bands of this bandwidth are contaminated by some aliasing due to the anti-aliasing filter not being perfect. So, in the case of non-ideal aliasing filter, there's interference. In the case of non-ideal anti-aliasing filter, I got a spectrum. I multiply by a low-pass filter. And what I could do then is if I actually filtered my signal, there's going to be kind of a trade-off here. The first trade-off is that I'm probably going to crop or attenuate some of my signal if I want to filter out exactly that bandwidth. Okay, so the trade-off is either I'm going to cut some of my signal or I'm going to allow some interference or noise to alias in. Okay, these are the natural trade-offs, right? So I filter, either I finish, I cut off here, but then, of course, something is going to be affected. Or if I extend my bandwidth, then this noise over here is going to alias back in. This interference over here is going to alias as well. Which side is going to alias to? Always the other side, right? Because it's the other replica that is going to be affected. Okay? So that is an issue, and it happens all the time, and there's ways to deal with this, but of course there's going to be a trade-off. You need to give something. Okay? Something got to give. So what we could do in order to mitigate with that is not to sample at the Nyquist rate, but sample more than the Nyquist rate. Okay, let's try to give that. Have a faster A to D conversion. And what would that give us? If I have the continuous time signal going, this is the usual A to D that we talked before, right? X to C goes into a sharp analog anti-aliasing filter, which is very hard to implement. That goes into a digitizing stage and then quantization. Instead, what we're going to do is we're going to take X to C, pass it through a simple analog anti-aliasing filter. For example, a second-order filter, right? Something that's not necessarily as sharp, that can easily be implemented by just a second-order system, pole system, for example. Then we're going to oversample the signal. So sample at a rate which is m times faster than the Nyquist rate that I'm planning to, then implement, instead of doing this filtering in the analog domain, which is difficult, we'll do a sharp digital anti-aliasing filter that can also compensate for some of the weighting that, or some phase response or something that would, that the simple analog anti-aliasing filter did. So filter it by pi over m, and then downsample by a factor of m, digitally. Okay? So that allows us to trade off here. There's always a trade-off. Here, we can sample at a low rate, at exactly the Nyquist rate, but we have to implement a really good anti-aliasing filter. Here, we don't use a good anti-aliasing filter, so we use a simple one. But then we have to operate at a higher rate, and then we have to do some computation in order to filter this extra signal out and then decimate. Okay, so there's the laws of conservation of work here, applying here. But the question is, what is more advantageous in terms of designing a system? And often the second case, for the flexibility of being able to not have to design a very sharp filter, you can do a lot of things in software. That's much easier to change. And so this is sometimes a much better trade-off. Okay? So you add some computation for the purpose of better sampling. So how does it work? What we're going to do, if we have a band-limited signal that we'd like to sample, this is really, the highest frequency omega sub n here. And ideally, we should sample it only at twice that high frequency. So sample it at 2 times omega sub n. Okay, that would be the Nyquist rate, right? But the problem is that, there's interfering signals, there's noise outside of this bandwidth. I need to filter that out before I sample. So I'm going to run through a low-pass anti-aliasing filter before, and that filter is not going to be as sharp. And instead of sampling at this rate, I'm going to sample at this rate. I'm going to sample at a faster rate than the Nyquist rate. So after low-pass filtering, so this is the rate I'd like to sample. After low-pass filtering, I'm going to get this signal. Notice that in this case, there's no distortions inside the signal, but of course they could be depending on the implementation. But the interfering signal is attenuated. That's one thing. And also noise is kind of attenuated till it really goes almost to zero. It drops pretty quickly as we go further away. Okay. So now I'm going to sample at this rate. So I'm going to get replicas every omega sub s, okay, after sampling. Okay. So am I going to get aliasing? If I'm going to sample at this rate, am I going to get aliasing? What's going to alias to where? Well, whatever's outside the bandwidth is definitely going to alias, right? So this noise is going to alias to here, right? Is it going to alias onto my signal? No. Right? It's not going to alias. And this is the whole idea. Okay? So after I sample, now you see from noise that is a little bit more pointy, means that it's decaying. Now this part aliases over here, and so I get this. Okay? So now the interfering signal is not overlaid on top of my signal. Okay? The noise outside of my spectrum also is not overlaid on top of my signal. Now what I could do, if I just want this part of the spectrum, what do I need to do now? Low-pass filter, but now we're in the digital domain, right? These are just samples represented on a computer, right? I can just type it down, right? Run it through a low-pass filter, and I'm representing here like an ideal one, but of course, again, it's not going to be ideal. But I can make it sharper, or to some specs, much easier than I could do with a bunch of capacitors and inductors, or maybe an op-amp, in order to do this, because those might change with temperature, right? This would not change with temperature, except if I'm feeling sick and I type the wrong number on the computer, then it would change, right? But that's it. That's the only temperature effect that it could have, right? Or the computer malfunction. But otherwise, it's not going to change. Right, because this is a digital system. Okay, so this is good. Okay. So now I get a signal which doesn't have the interference in it. It doesn't have noise aliasing in as well. And so I get exactly what I want. Okay, so by oversampling, trading off that, so I need to have a faster analog to digital conversion. I don't get this. I can use a crappier anti-aliasing filter, and then still sample it at an oversample rate, then digitally filter. So I split my system into two now. Okay, I move some of the operations to the digital domain, which is much easier to implement. Okay, I still need the anti-aliasing filter in the other domain, because otherwise noise is going to go over my signal, and so that's not going to be good, or interference is going to go over my signal. So I still need to do some filtering in the analog domain, but it doesn't need to be as complex. All right? Questions? All right, so now we're going to dive a little bit. Does it make sense? Now we're going to dive a little bit into probability. Okay? And we're going to keep it at, I think, a comfortable level, but I think it's worth describing you the things that nobody tells you so far is we have to quantize. What is the effect of quantization? I mean, definitely I'm introducing errors. How these errors in the quantization translate into errors in my signal? Because when I quantize and then I want to reconstruct, it's not going to be the same, right? So far we didn't even account for any quantization problems, right? But now we're going to quantize. And I can quantize and decide, yes?
Sorry, could you clarify what's the difference between quantization and sampling?
All right, sampling is taking something continuous, right, and evaluating it at a discrete number of points. But the representation of that could be continuous, infinite, like a continuous number. But then I want to store it on a computer. Let's say I'm going to store it in 16 bits, 32 bits, 64 bits. Pick up your precision, but it's going to have a certain precision. So that precision is limited. What is the consequence of an A to D being 8 bits, 12 bits, 14 bits, 16 bits, 24 bits, 1 bit? Right? What is the consequences on the signal itself? Okay? So there's definitely going to be some consequence, right? Because we're approximating it using some discrete number of bits, a finite number of bits. Okay? So bear with me here, right? So here's the model. Okay? We're going to model this in a particular way. So X sub C goes into C continuous to digital, right, with a certain sampling rate, and we're going to get X of n. This is still this is discrete time, but continuous representation, like infinite precision. Then I'm going to quantize it. Okay, this is our model, and I'm going to get X hat of n. That's the quantized. So if I've got a sinusoid coming in, right, and the values of the sinusoid where I evaluate, those are the big circles. See? Big circles. Big circles. Big circle. I have a certain dynamic range of the signal that comes in. The dynamic range of it, I'm going to define it as 2 times X sub m. Okay? Basically, if this goes to plus minus some value, it goes to plus minus xm in terms of voltage, for example, or current. Pick your pressure of, air pressure or whatever. Pick your value. It goes from plus minus, from minus xm to plus xm. That's the dynamic range of my signal. I'm going to break that dynamic range into delta intervals, okay? Representing, the quantization portion of it. Okay? So if I broke it into 4 bits represent 2 to the power of 4, which is 16. So it will break it into 16 portions. So with 4 bits. With 8 bits, 256, and so on and so forth. Okay? So those are the values that, the definitions that we're going to be using. So instead of actually storing this value, I'm going to be storing this value. And instead of storing this value, I'm going to store this value. Instead of this one, I'm going to store this one, and so on and so forth. Okay? So I'm storing something that has an error. All right? This is not perfect now. Okay? So 61C. Woo! Right? 61C. For a 2's complement representation with a number of bits, which is b plus 1, okay? B plus 1, when the value of the quantize is between minus 1 and 1, right? That's how we're going to define it. Okay? Then delta, or the size of each one of these quantization between these small intervals, right? The quantization, the finest accuracy that I can represent something is going to be 2 times xm divided by 2 to the power of b plus 1, right? Because this is the number of bits that I have, b plus 1. That's how many pieces I'm going to break this interval, which is 2 times x of n. Okay? So I'm breaking 2 times x of n into these intervals. So that gives me delta to be x sub m divided by 2 to the power of b. Okay? Yes? It's a definition. It just makes the numbers nicer. Okay? It's just plus minus something. Instead of, going from minus half to half or something, we just divide it to be plus minus x of n to x of n. That makes the numbers, but actually it's not a big issue. Everything will cancel at the end. So x hat would be, effectively, the range, right? My range multiplied by the quantized value. Okay? So what the sample that I'm storing is the quantized value, which is between minus 1 and 1, multiplied by the range. Okay, and this is why we define it that way. Okay, great. Any questions up to here? Right, there's no probability here. This is everything deterministic. Okay? So here's where things, and this is actually the beauty of this analysis, and I think it's due to Whitrow, is that we're going to model, this is really hard to model, right? So x of n comes in, it quantizes, and you get this. What we're going to do now is model this as a random process. Okay? We're going to model this as x of n coming in, which is accurate, and then some noise signal, which is the error between the quantized version and my non-quantized version, that it's added here, that will give me the quantized signal. Okay? So the quantized signal is the original signal plus some error signal. And that error, actually this is not even random. This is right now an error signal, which I can basically corrects everything and moves it to the right places. So, the error signal will be the difference here, and this difference, and this difference, and so on and so forth. Okay? So in that case, the error signal is bounded between minus delta over 2 to delta over 2, because this is how we round the numbers. Okay? So it's bounded between them, and it's equal to this and less than this. So x of n, the original one, is bounded between minus x of m minus delta over 2 till x of m minus delta over 2. So this is the range of the original signal. Okay? Does this make sense?
Should that be plus delta over 2 on the right?
Maybe. It won't matter, actually, but yeah, you might be right. I'll have to check. So what we're going to do now is model this E of n as a noise process. And the question is whether that modeling is correct or not. Okay? But right now we're going to assume something about that process. And pay attention because it's really important. Okay? So E of n is going to be sample sequence of a stationary. It means that statistics doesn't change over time. Random process. We're going to assume that E of n is not correlated with the signal. Okay, so the error is not correlated with actual input. Is that true? It's actually not a bad approximation, depending how many bits you have. But we'll see that. So if I look at the expectation between, or the covariance between E of n and x of n, it will be 0. We're also going to assume that E of n is not correlated with E of m when m is not equal n. Okay, so each evaluations of these E's are not correlated to each other. Okay, so this is an IID, independent, identically distributed noise process. Okay? And of course, then in that case, we can assume that E of n is some random variable that has a uniform distribution between minus delta 2 and delta 2. And it kind of makes sense. It could be anywhere in between, and there shouldn't be any preference whether it's going to be, it shouldn't be Gaussian, right? For sure not, because it's really just bounded between minus delta 2 and delta 2. Once you define it that way, we know what the variance of that one, right, of that value is, right? So the variance of a uniformly distributed random variable is delta square over 12. Right? In that case, we know what delta is, right? We calculated it, right? It depends on x sub m, and it depends on the number of bits, right? So now the variance is 2 to the power of minus 2b multiplied by x sub m squared, all of that divided by 12. That's because delta is 2 to the minus b x sub m. Okay? So it turns out that this assumption really works well for signals that don't change rapidly with respect to your sample. Okay? The opposite. That changes really rapidly with respect to your sampling. And it kind of makes sense because if you have something that changes really slow, of course they're going to be correlated. The errors are going to be, similar to each other. But if my signal changes really rapidly, then all the quantization error are going to be quite different. Okay? And also, we need a signal that is not clipped as well. Okay? So it doesn't reach the maximum and so on and so forth. So here's an example. This is from the book, okay, of a quantized sinusoid signal. And this is the quantized sinusoid signal when it's quantized. So it kind of looks like a sinusoid, but it's not really a sinusoid, right? And that is quantized to 3 bits. Okay, 3 bits is quantized into 8 values. In that case, the error looks like this, and it doesn't look so much random, right? It looks quite correlated. But when you quantize here to 8 bits, that could look like something random that has statistics that's approximately uniform. And if you actually plot the histogram of this, it would look pretty much uniform. Okay? And not correlated. If you look at the autocorrelation of this sequence, you'll see that it looks almost like a delta function. Okay? Which is effectively means that it's uncorrelated. Yes?
So you said that it's a good model when the signal doesn't change rapidly?
It changes rapidly.
It changes rapidly?
It does change rapidly with respect to your sampling, and the quantize are small. So
I think, don't we also want to sample really fast? So it would change.
So if it changed really slowly and you sample really fast, that's a problem. Because then you'll get errors that look like this.
But isn't that what we're doing when we oversample?
When we oversample, that's actually what happens. So you might want to, in order for this model of modeling that we're going to do to be actually applied, then you're going to start deviating from the model a little bit. You're going to get more correlated type of errors. They're not going to be as uncorrelated. But if the quantizers are small, then that will be fine because that will be broken into smaller parts, which are going to be more random. So then you maybe need a little bit better bit accuracy. Okay? But as long as, this actually model works pretty well when we're talking about more than 6 bits, okay, at Nyquist rates, and even above Nyquist rates. So it is pretty good. It's not perfect in this case, but it's still not too bad. Okay? All right. So effectively now, we can think of the quantization error as noise. Think about this. We can model this as noise. Now we can talk about, how much signal to quantization noise ratio is and how accurate our measures are in terms of SNR. So effectively quantizing the signal, you're adding noise to it. Effectively. That's what you're doing when you're quantizing your signal. You're actually adding noise to it. Crazy, right? But the cool thing is we can calculate how much noise you're adding to it. So you can, for a certain SNR that you're capturing, maybe you don't want to quantize more than the signal-to-noise ratio they already have in the original signal, because that would be wasteful. Okay? So for a uniform B+1 bits quantizer, so it's a uniform quantizer. If you don't do a uniform quantizer, the analysis will be very different. Okay, so we're talking about uniform quantization, where the variance is given by this. The SNR of the quantization is 10 log 10 of the standard deviation of, or the power of the signal that's coming in, divided by the standard deviation of the quantization signal, or quantization noise. Okay? If this is the quantization noise, then that ratio would be 10 log 10 of 12 times 2 to the power 2b sigma square x, which is the variance of the input signal, divided by what is my dynamic range? X sub m square. Okay? Because this is a log of something that is multiplied together. In dB, it's nice because just things add together. So what you get, basically, is a penalty of 6 dB, or an improvement of 6 dB in the quantization, in the signal to quantization noise ratio, improvement of 6 dB per bit. So every bit that you give me, you get an improvement in signal to quantization noise of 6 dB. Factor of 4 improvement. Okay? Plus a constant number, which relates to the log 10 of 12, which is 10.8, minus 20 log 10 of the quantizer range divided by the RMS of the amplitude, root mean square of the amplitude of your signal. Okay, so sigma x is really the root mean square of your amplitude of your signal. So what does this mean, actually, if you think about this? This is loss of SNR, right? Kind of makes sense. If my signal only varies, like this is my dynamic range that I'm going to be digitizing. If my signal only occupies a small part of that dynamic range, then I get a hit because I get more quantization. I need to scale my signal before I go to ADD to the maximum dynamic range of the ADD to satisfy it. Okay? So if my signal is too small in amplitude, that's going to hurt me when I digitize it. That's why I need preamps. Preamplifying a signal before I do ADD conversion, so it is always scaled to the right dynamic range of the ADD converter. Otherwise, I'm adding quantization noise. Cool, huh? It's a really cool analysis. So this is what we get. So improvement of 6 dB every bit. Every bit that you give me, 6 dB. So that's significant. Bits. Turns out getting more bits is a lot more power too in the ADD conversion. So there's a trade-off there. Okay, there's always a trade-off. The range of the quantization must be adapted to the RMS amplitude of the signal. Otherwise, we get a hit from this. Okay? So there's a trade-off there between clipping and noise. So if my signal, varies, very slow, but then suddenly, it grows up, then I need maybe to scale my signal to the maximum, right? So it doesn't get clipped. But then I get a lot of quantization noise in the places where it doesn't vary much. Okay? So that could be an issue. So you can think of a case where, first of all, you need a preamp in order to amplify if my signal is really too low for my ADD. So every ADD, it quantizes a certain voltage into bits. So if the range is, 2 volts, plus minus, for example, then I need to make sure that I amplify it to that range. Or I attenuate it to that range so I don't get clipped. And then if my signal changes over time, it's not stationary, and speech is not stationary, and other signals are not stationary, then I might want to use an analog auto gain controller, or AGC, that would change the gain of my amplification such that I get the better quantization. Then I can account for that digitally if I know what the value of the gain is. Okay, so I can really get back the scale, but I don't get the quantization noise. Okay, so if sigma x, which is the root mean square of my signal, how much my signal changes, is about 1/4 of the dynamic range. So my SNR, my quantization SNR, is going to be 6 times the number of bits, approximately, minus 1.25 dB. Then if I want to get an SNR of about 90 to 96 dB of signal to quantization noise, I need 16 bits. And that's why audio has 16 bits, because you want really good, high-quality audio in CDs. So the signal to quantization noise in CD is about 90 to 96 dB. Okay? Cool, huh? Any questions? Yeah.
What is the example for why is the
Pardon?
The delta X,
It's kind of a trade-off, right? Because, the RMS is kind of the root mean square, right? My signal does, become bigger than this, right? So you want to make sure that you don't clip. When you clip, you're actually introducing way more errors. You never want to clip. All right? Cool. But then I said before, what about oversampling? I mean, I need to do oversampling in order to compensate for the anti-aliasing filter, right? How does that affect my quantization noise? Well, let's take a look. In the case of oversampling, I got a signal, and I'm oversampling by a factor of m. So now I'm sampling factor of m faster than the Nyquist rate. Then I get quantization noise into the system. So this is what I have. Then I'm going to low-pass filter it, and then downsample to get the decimated signal. And the question is, what is the signal to quantization noise then? And you're going to be surprised. It's going to be really interesting. So x sub c j omega is this signal that I want to sample. I'm going to sample at a factor of m faster. So this is the DTFT of x hat. It has a component that relates to the signal. Its amplitude now is multiplied by, if this is 1, it's multiplied by omega sub n m over pi. Okay, it's really the t, which is the sampling rate. Okay, t prime, that was the sampling rate. So that's that's its amplitude. Now here's a question. Does the quantization noise has anything to do with the sampling rate? Except for the statistics that might change. But let's assume that this is not an effect. Is there anything in the analysis of the quantization noise, in its terms of its variance or its power, has anything to do with the sampling rate? It had the bits. It had x of m. Did it have anything else? Was omega there? No, right? It's nothing, right? So that means that the variance of the quantization noise is going to be independent of the sampling rate. It's always going to be a variance of basically the same variance that we calculated it. Right? So the variance is going to be exactly the same. What about the peak of the signal? It depends on something. Right? It depends on m. So for higher sampling rate, this will go up. What about the bandwidth of the signal, the digitized signal? What's going to happen to that? It's going to narrow down. Right? What about the energy of the entire signal? Is it going to change? Parseval. No, it doesn't change. The energy doesn't change as long as I sample it at least above the Nyquist rate. I get a perfect representation. So the energy of the signal doesn't change. It is concentrated in a small bandwidth in the digital domain. But noise is always spread, which means that if I low-pass filter and then decimate, what happens to all this noise? What's happened to all the noise? Right? It's filtered out. Okay? What is the power of the noise? It's just the noise that is overlapping with our signal. So it's the integration of sigma square over that bandwidth. Hence, when I downsample, my signal is going to be omega sub n over pi in its amplitude. And the noise is going to also scale down by a factor of m. Is going to be sigma e squared divided by m. So my signal to noise to quantization noise ratio is going to improve as I oversample. How much? By a factor of m. Okay. So in an oversample ADC, the energy of xd equals to the energy of x of n. So the decimated sample signal is the same. We don't filter the signal, but the standard deviation of the noise is reduced by a factor, actually a square root of m. The noise variance is a factor of m. The standard deviation is actually the variance. The variance is reduced by a factor of m. So now if I write the quantization, the SNR, the quantization SNR, I get this extra component here that is 10 log 10 factor of m. Effectively, every time I double the sampling rate, I get 3 dB improvement in signal to quantization noise. Every time I double the sampling rate, 3 dB improvement. So 4 times, I get an extra bit. Okay? Every time I oversample by factor of 4, I get the equivalent quantization error as if I added another bit. Okay? Because I can oversample and then filter digitally and improve basically my signal to noise ratio by that. Okay? So doubling of m gets you 3 dB, which is half a bit of accuracy. So with oversampling of 16 with an 8-bit ADC, we get the same quantization noise as a 10-bit ADC that is sampled at the Nyquist rate. Yeah.
What about the fact that oversampling effectively makes your signal move more slowly, so that there is correlation?
Yeah, we ignore this analysis, and for certain deltas, it doesn't. You don't see that effect. But of course, if you had a 1-bit quantizer, right, and you sampled it at 1,000,000 times faster than Nyquist rate, turns out you will be able to reconstruct your signal quite well. You will. With a 1-bit quantizer, you will be able to reconstruct your signal quite well. You can think of it from the digital to analog. There's a pulse width modulation, like the Arduino does that, where over a certain range, so if you want to produce like a half a volt, like half the maximum of output, then the Arduino would basically put a voltage over half a cycle and then off. And then if you want a quarter, then you turn a voltage on for a quarter of the time and then 3/4 of the time off. If you put a low-pass filter after that, you get a okay digital to analog converter. This is the opposite, where you have some voltage changing in and then you quantize it to either 0 or 1. It's exactly the opposite. Then you can filter it digitally. Okay? So ADC A lot of ADCs are actually implemented in the way that, like if you want a 12-bit ADC, what they do is they sometimes do an 8-bit ADC, and then they oversample, and then filter for you. So some of them are implemented that way too, right? But you get the equivalent of a 10-bit ADC. All right. So in the last 5 minutes that I have, I want to talk about practical ADCs. The previous sentence that I meant, it was, analog to digital converter. Is that what I want to talk about? I think I want to talk to digital to analog converters, but anyway, I think this is wrong. Digital to analog converters. Okay, so in the digital to analog converters, I have x of n, which is discrete time, and I need to convolve it with a sync pulse. We basically convolve it with syncs to generate the reconstructed signal, which is continuous time. Okay, so my reconstruction is really a scaled train of sync pulses, okay, that are delayed in time. So of course it's difficult to implement because the sync is just too long. You cannot. I mean, it's really hard to do. So what instead people do is do the following. They take the samples and then they convolve with this interpolation filter, which is finite. Then you go through a reconstruction filter, an analog reconstruction filter that compensates for the fact that you use the finite length interpolation filter. Okay? Here it's digital. Here it's continuous. Here it's analog. Okay? So in that case, if h of 0t is finite, it's really easy to implement. For example, zero order hold. That's really easy. You put a voltage, and then if you need to change a sample, you just jump, right, and put a different voltage, right, in this way. So we could do that. That's easy to implement. Now it's digital to analog conversion, right? This is analog after that, but then it's a crappy reconstruction. So instead of the scrappy reconstruction, we need to filter it to make it better. So the Fourier transform of a zero-order hold, basically convolving with this thing, is really convolving with a sync. Okay? Or, multiplying with a sync in the frequency domain. So convolving with a rect in the time domain, multiplying with a sync in the frequency domain. So zero-order hold interpolation is effectively, instead of doing this sync interpolation, you basically hold it, and then when the next sample comes in, you change the voltage. You hold it, change the voltage. Hold it, change the voltage. Okay? So it is a convolution between x of 0 and really the impulsive version, x of s. Remember x of s, which is the impulse train? It's exactly the same. So in the frequency domain, it is the multiplication between the Fourier transform of this zero-order hold filter and the frequency of the sampled signal. Frequency of the sampled signal is the original signal that is replicated, right, and then multiplied by a sync function in the frequency domain. So it looks like this. The output of, so what we have is x of s, that's the replicated signal. That's the Fourier transform, the impulsive version of my digital signal. This is the interpolation filter, which is the zero-order hold. And in the frequency domain, it's just a sync. Okay? And then I multiply it in the frequency domain by a reconstruction filter to fix things. So if this is the replicated signal, what I really want to do is just do a low-pass filter, right? But I don't. Instead of convolving with a sync, I convolve with a rect. So I get a multiplication with this thing. So of course, some of these side lobes, or the other replicas, will stay. But really, what I want to do is to convolve with a sync overall, right? So what I do is I do an analog filtering with a reconstruction filter such that this multiplied by this will give me a rect. which is going to look like this. So again, ideally, I'd like to do that. I can't. I do that. So I got these left. So instead, I take this and I multiply by something like this that will give me this. So then I multiply again by another, effectively with an analog filter that looks like this. Okay? Now the problem is that it's really hard to generate an analog filter that looks like this. So what I'm going to do is maybe upsample, spread these a little bit away, then do zero order hold, which now produces something like this, and then filter with something that is not as sharp in the analog domain. So if this is an easier implementation with analog components, and this one need analog components made of lossless non-obtainium components, then I would prefer this. So again, in the reconstruction process, I can use upsampling in the digital domain and then use a faster digital to continuous, right? A faster DAC, right? That's a trade-off again that can produce this zero order hold. Then use a low-pass filtering, which is made of maybe ATC capacitors and some, maybe some, some other components which are obtainium. All right? So with that, I think we'll finish today. And we're going to switch to a different topic next time, which is, I think, if I'm not mistaken, filter design. But I'm almost positively sure. See you on Friday.